Okay, so we're going to take a look at stoichiometry. So here's a balanced chemical equation. What we see as chemists is I have 4 iron solid. Okay, so iron, if there are 4 atoms of iron, they are going to react together with 3 oxygen molecules. So each of those has 2 oxygens to give me a Fe2O3, 2 Fe2O3 solid particles. So this is actually rust. Okay, so you're going to produce rust. So those things are going to combine together and give you these compounds. It balances out. There's 4 oxygens on each side. There's 6. There's 6 oxygens. There's 4 irons on both sides. This is what it looks like. But we can't really think like that. The way that we actually have to see it as chemists is it's not that I have 4 molecules or 4 atoms of iron and 3 molecules of oxygen. What we really have is I have 4 moles of iron and I have 3 moles of O2. Gives me 2 moles of rust or iron 3 oxide. Because our chemical world is tiny. So anytime I have a reaction, we have to think in terms of moles, which is essentially just counting, right? We ignore this 6.02 times 10 to the 23rd, and we just think in bulk numbers. So a bunch of iron, 4 bunches of iron react with 3 bunches of oxygen to give me 2 bunches of Fe2O3. So when we're looking at stoichiometry, we're really counting, if I start with this many moles, how many moles of something else will I end up with? And so it's just simply a ratio. So what this means is another way that we could say this is 4 moles for this balanced chemical equation. 4 moles of Fe is equal to 3 moles of O2, which is equal to 2 moles of Fe2O3. Okay, so there's the ratio there that if I start with 4, I'm going to need 3 of the oxygen to give me 2 of the product. Okay, so that's the kind of thing that we're looking at. But we never have like 4 moles of iron is quite a bit. We're going to give you we're just going to give you a small quantity. So we might say, all right, well, you have 0.13 moles of or MOL, because we usually just moles of iron. I want to know how many moles of, I don't know, O2 do I need to react? So that's the question. And these are just simple conversions. This is, so I'm going to take my 1.13 moles of iron. I'm going to set up a conversion so moles of Fe cancels, and I'm going to have moles of O2 on the top. I can do that because in this balanced chemical equation, 3 moles of O2 is equivalent to 4 moles of Fe. And so we know that it's for every 4 moles of Fe, I'm going to need 3 moles of O2. So we expect this number to be a little bit smaller. And again, I'm going to just kind of walk through what I do for these calculations just so we can keep it square. So 0.13 moles of iron times 3 divided by 4 gives me 0.0975. Oh, that went away. There we go. 0.0975. Actually, I only need 2, so 0.098 moles of O2. And that's how many I end up with because moles of iron cancel. And that makes sense because I have a 3-to-4 ratio. I need more moles of iron for less moles of oxygen, and that's what we see play out, 0.13 to 0.098. And we could do that same thing. So my question for you is, if I start with 0.013 moles of iron, how many moles of Fe2O3 will I end up with? Okay, so go ahead and do that math, pause this, do that quick math, and see if you can set it up properly. And I'm going to keep going right now. So I want moles of iron to cancel, so I'm going to put that on the bottom. I want moles of Fe2O3 to prevail. So for every 4 moles of Fe, 2 moles of Fe2O3. It's basically half. So 0.052, 0.052, right? Yeah, 0.052, 0.13, 2, yeah. Oh, 0.065, sorry, my math. All right. There we go, 0.065 moles of Fe2O3. So again, what we have just done is we call this right here, this is called molar ratio. So it's the molar ratio from the balanced chemical equation. We always use molar ratio to convert from one chemical to another. So we're converting from one chemical to another using molar ratio, okay? We do that because we have to speak in moles, because that's what a balanced chemical equation is. It's always in moles. Okay, so with that said, I'm going to take this equation and we're going to talk about it in a little more detail. So I have this equation. Unfortunately, we're never given moles in a lab. I don't just hand you, oh, here's 3 moles of iron. What we usually say is, all right, I am going to give you 10 grams of iron solid, and I want to know how many grams of rust or Fe2O3 am I going to end up with? So that's the question. So I give you, because you can weigh grams in the lab. Grams are tangible. It's a mass that is tangible. So if I start with 10 grams of iron, how many grams of iron oxide? So at some point, I have to convert from the chemical to another. And we unfortunately cannot go directly from grams of iron to grams of iron oxide. So we're going to use what I call the stoichiometric square, where essentially you start with gram quantity. And in order to use this to go for the balanced chemical equation to go one for the other, we know we need to use molar ratio, so that means we need moles. So the first step is always to say, okay, I want to convert from grams of iron to moles of iron. And I'm going to write down all the information that I need here. So moles of iron. Okay, so the question is, what is the molar mass of iron? And of course, you have to look up the, on the periodic table, if you look up iron, you see that, okay, the molar mass of iron is equal to, Fe is equal to 55.845 grams per mole. So that's going to allow me to convert from grams to moles. Okay, so that's the first step. And so let's do that. So first step is to convert from grams to moles. Let's get that done. So if I start with 10 grams of iron, I'm going to set it up so grams of iron cancels, and I've left behind with moles of iron. So for every 1 mole of iron, I have 55.845 grams of iron. Do the math. Again, saying it out loud, 10 divided by 55.845 gives me 3 sig figs, so 0.179. 0.179. And then what's my unit? Those cancel, moles of Fe. Great. So I have 0.179 moles of iron. 1.179 moles of iron is getting us part of the way there. Now that I have moles of iron, I can convert into moles of another substance in that balanced chemical equation. So I can now go from moles of iron to moles of Fe2O3. We use, again, the molar ratio. This is step 2, molar ratio to do that. And what I can discern from the molar ratio up above is 4 moles of iron gives me 2 moles of iron oxide out. So 4 moles of iron is equal to, for this balanced chemical equation, 2 moles of Fe2O3. So I can take my gram quantity of 0.179 moles of Fe, and I can set up another conversion. I want moles of Fe on the bottom. I want moles of Fe2, what I'm looking for, on the top. Again, I always want my moles of the thing I want to cancel. And we know based on the balanced chemical equation that 2 moles of Fe2O3 and 4 moles of iron is what we end up with. So in the math arena, so first of all, moles of Fe cancel, and my units left are moles of Fe2O3. And so 0.179 times 2 divided by 4, or just divided by 2, 3 sig figs gives me 0.0895, 0.895 moles of iron, iron oxide, 0.0 iron 3 oxide, 895 moles of Fe2O3. Great. So we are almost there. The last step is just simply saying, all right, well, now that I know how many moles of iron oxide I have, I need to use the molar mass of Fe2O3, which is equal to, let's see, 159. Yeah, 159.69 grams per mole. So this last step is going, so molar mass to get to moles, molar mass to get to moles, molar ratio to get to moles to get to another substance, and then molar mass to get back to grams. So we're going to be doing a lot of molar masses on either end. And I'm going to point something out in just a second. So this was step 2. Step 3 is taking that molar quantity of 0.0895 moles of Fe2O3 and saying, all right, well, now I can get rid of the moles and convert it into grams. So 1 mole is equivalent to what I say, 159.69 grams. Moles of Fe2O3 cancel, and we are left with what? Times 159.69 grams, 14.3. Oops, undo. 14.3 grams of Fe2O3. We've done it. We went all the way there. So again, use molar mass, then we use molar ratio, then we use molar mass, ratio, then molar mass to essentially go around the horn, go from one substance to moles, moles to moles. We do that through molar ratio, and then moles back to grams. What I want to point out is whenever I'm doing molar mass, notice that it's only 1 mole of the substance. Never look at the balanced chemical equation when we're doing molar mass conversions. If you're going from grams to moles, I don't care what the coefficient is in front of the chemical. That does not matter. So this is all pretty tedious to kind of go through these steps one at a time. So I'm going to show you the quicker way to do it, and then I'll let you do it for oxygen. Okay, so I know if I start with 10 grams of iron, I end up with 14.3 grams of iron 3 oxide. Let's do this, the quick version of this. And instead of, what you'll notice is I solve for moles and then I write the number again, then I solve for moles and then I write the number again. So I have written this number once here and then here, written this number once here and then here. We can just do all of these in line like a multiple conversion. So let's start with our original number of 10 grams of Fe. I'm going to set up all the units and then I'm going to plug everything in. So 10 grams of Fe. So first thing I want to do is grams of Fe here, and we know I need to get to moles. So that is step 1 that we're going to do. And in order to do that, I need the molar mass of Fe, and we're going to get to that in just a second. Next step, I need to go from moles of Fe to moles of Fe2O3. And that is done, that's step 2, and this is molar ratio. Right. Next up, the last step, I want moles of Fe2O3 to go away. and I want grams of Fe2O3 to prevail. This is step 3. We're using molar mass of Fe2O3. What you can see is grams cancels, moles cancels, and I'm left with my gram quantity. So we set this up, and if you set it up this way, we know that we're not going to mess up our calculations. Okay, so what I want you to do is recognize when we're dealing with a molar mass, 1 mole, those have to be equal to 1. Maybe just put those in there. And I know that grams of Fe, so molar mass of iron is 55.845. Okay. And we know that for every 4 moles, again, going back to the balanced chemical equation, for every 4 moles of iron, I get 2 moles of Fe2O3. So it's a 4-to-2 ratio. So 4 moles of iron is 2 moles of Fe2O3. And then I know that 159, because it's right above there, 0.69 grams of Fe2O3. Okay, so now to do the math. Again, I'm going to walk through my math for this. So 10 divided by 55.845, enter, times 2, enter, times 4, or divided by 4, sorry. Divided by 4, enter. Oh, whoops. Yeah. Okay, it's wrong keystroke. Okay, so times 2 divided by 4 times 159.69. As we do it all the way across, we do come out with the same answer. Thank God. 14.3 grams of Fe2O3. So again, we are proceeding just across, and we do all of those steps in line as opposed to doing them kind of one at a time. Okay, so it's much easier to do it that way. So my question to you is, all right, so if I start with 10 grams of iron, I'll just put this bullet down below because I'm going to use it in a second. If I start with 10 grams of iron, how much oxygen am I going to use? So 10 grams of iron. So again, same idea here, and I'm just going to set this up. Again, we can always set this up. So I encourage you to pause it, plug in your units, see if you're right, and plug in your values, see if you're right, and see if we can get this kind of squared away. Okay, so here we go. I want grams of iron to go away. I'm going to put that on the top. We always are converting to moles first, and I do that through the molar mass of iron. In this case, it's actually just above, so 55.845 grams per mole. Next, I want moles of iron to go away because we always want that. And I want moles of O2 to prevail. Okay, so I want to end up with moles of O2. And we do that through molar ratio. And if we look at the bottom, we're going to be able to calculate that. So, but I'm going to finish units first. I want moles of O2 to go away and grams of O2 to remain. And that is going to be the molar mass of O2, which I know is 32 grams per mole. Okay. So next up, we're going to plug in the units, see if you can give this a go and plug in the units properly. Okay. So again, whenever we're dealing with molar masses, the moles are always 1. Never put a coefficient in front that's in a balanced chemical equation when we're dealing with a molar mass. 1 mole of Fe2O3 is equal to 55.845. 1 mole of O2 is equal to 32 grams-ish, okay? So the last thing is molar ratio. If I look below, moles of O2, there's a 3 in front, fantastic. 3 moles of O2 for every 4 moles of iron. And there we go. And again, the math, let me just walk through how I would do it. 10 grams divided by the 55.845, enter. Times 3, enter. Divided by 4, enter. Times 32, enter. 4.297, so round it to 3 sig figs. We end up with, actually I can use that right there, 4.30 grams of O2. That's my final answer there. So there we go. Okay, so we have solved this. We have done it. Now, here's a little trick. So we did all of these calculations, and what I know is if we look at the balanced chemical equation, I said moles work out on both sides. I say we have to end up with the same iron on both sides, same number of oxygen. What that means is the masses actually have to be the same on both sides. So the mass of the total mass of reactants has to equal the total mass of products. Those two things have got to be equal to one another. Okay, so if they're equal, when it comes down to just having one left, we can actually always just plug in those values. So remember, I started with, and we'll use blue here, I think. I started with 10 grams of iron plus, and we figured out that we ended up with 14.3 grams of Fe2O3. Well, it turns out I actually didn't even need to do this last one because I know once I have only one that I'm not sure of, I can figure that out. This is 4.3 because these two together are 14.3 grams to the 14.3 grams we had as product. So you should be able to add both sides up once you only have one left. You have to do stoichiometry until you have one left. You can always check your answer with stoichiometry, but a quick way is the last one. You can always do law of conservation of mass. The mass of your reactants equals the total mass of your products. Okay. All right. So that's pretty much it. That's me walking through stoichiometry. Hopefully there's a bunch of problems that you can do, and I'm going to upload this as well. So sorry it took me so long to get it up. I can't end it. Here we go. One more time. And